Hello everyone, my name is Ferhat Özgür Çatak. I am an associate professor at the University of Stavanger in Norway. My presentation title is 5G spectrogram-based random number generation for devices with low entropy sources. You can find my implementation, my source code from my GitHub repositories. My username on GitHub is ochatak or okatak, so you can download the implementation of this work. Okay, first I want to start with the random number generators. Random number generators, we are using random number generators or shortly RNGs in cryptography. We are using RNGs for key generation, encryption, procedures, and also key exchange protocols. Basically, there are two different random number generators. The first one is true random numbers, and the second one is pseudo-random numbers. So what is true random numbers? We can obtain the true random numbers from the physical sources like cosmic rays, quantum fluctuations, spray from crashing waves, people rushing to catch trains. Okay, these are the true random numbers. We can obtain true random numbers from these physical sources. The second type of RNGs is pseudo-random numbers. So the generator, the RNG, could be a mathematical function or computer program that produced a number each time it called. So here, instead of a physical sources, we are using a mathematical function, a application, a software, or a device to generate the random number sequences. So there is a key difference between true RNG and pseudo RNGs is that pseudo random sequences generated by the pseudo RNGs eventually repeat, while true random sequences never repeat. So there's an example here. Let's assume that we have a application, a mathematical function, and this function generated these sequences. As you see, the period of this sequence is 5. So each 5 items would be repeat in this sequence. So it starts with 3, 3, 1, 9, 2, 4, again 3, 1, 9, 2, 4, 3, 1, 9, 2, 4. Of course, it's just a simple example to show the difference between pseudo-random numbers and the true random numbers. In real-world applications of the pseudo-RNGs, this period is very large. Okay, so the next step is to calculate the randomness of the generated sequence. So, for example, yes, let's assume we have a generator, and this generated created this sequence, random sequence, 51, 21, 45, and 3. So the question is that is the random sequence. So how can we measure the randomness? So as a starting point, we can use the entropy from the information theory. So, you know, the entropy is a measure of uncertainty of a random variable, or entropy can measure the amount of randomness in a message. In this case, the entropy can calculate the uncertainty or amount of randomness in generated sequences. Okay, the next one, yes, in my previous slides, I said that we can basically we can divide the random number generated into two types. The first one is true one, and the second one is pseudo ranges. Also, we can divide or we can classify the pseudo random number generated into two types: PRNGs, normal PRNGs, and cryptographically secure pseudo-random number generators. So let me start with PRNG. So yes, we are still using the normal pseudo-random number generators for non-cryptographic applications. For example, let's assume that you are working in a software development company and you are developing some applications or one module for a social media website, for let's say for Instagram or Facebook, and this application is responsible to show some random images to the social media users. So in this case, it is obvious it's not a cryptographic application or it's not a security related application. So we can use PRNG, pseudo random number generators. Okay, so in this case, in a non-cryptographic applications, we we have to use PRNGs. But there's another pseudo random number generator which is cryptographically secure. So what does it mean? Cryptographically secure PRNG is both forward and backward secure. So it means that one attacker cannot create the future or past random values from the observing the random values. Okay. So in our computers, in our servers, in our devices, mobile phones, tablets, etc. So we are using, operating systems. There are different operating systems. So our computers or our devices are capable to generate cryptographically secure PRNGs. How? So let's assume that we are using a Linux or Unix or Mac, Unix variant operating systems. In this kind of operating systems, there are two functions. The first one is random, dev random, and the other one is dev urandom. For Windows, there's a special API which is crypt generate random. Okay. As you see, there are several functions, there are several procedures to create the secure random numbers in operating systems. But in order to generate a secure random numbers, you need entropy pool. So, what is entropy pool? These devices, or sorry, these functions or these applications, these algorithms, there is only, not only, but the most important input parameter is the seed value, entropy value. So these functions, for example, dev random or in Windows crypt generate random function will take a seed value from the entropy pool and will this application will generate the random number. So each operating system has an entropy pool. So the operating system, when you turn on your PC, when you turn on your device, the operating system will start to create some seed values, and it will put this seed value into the pool, into the entropy pool. But when you generate a secure random, you will consume one of the seed from this pool. So in order to create this pool, the operating system use several inputs like keyboard strokes, interrupts, hard disk read address, mouse movements. So because they are unpredictable, so they are somehow chaotic. But after that, again, operating system will use these inputs, these keyboard strokes, discretes, etc. So it will create a seed, and then this application, these procedures, let's say crypt generate random API, will use this seed to create chaotic outputs, chaotic, unpredictable outputs. The output should be chaotic and unpredictable because there are several attacks, AI-based or artificial intelligence or deep learning-based attacks. So the attackers can generate or create a deep learning model, one machine learning model, and this machine learning model can extract the pattern, sequence pattern of the random number generators. So again, the output should be chaotic. Okay. So let me move to another side, 5G, or Yes, 5G wireless communication system. So in 5G networks, we already start to use the IoT services and applications. There are lots of connected cars, smart homes, industrial automation systems. So there are lots of advantages of 5G wireless communication systems. It provides higher data rates, lower latency, distributed architectures, and higher capacity. But on the other hand, there is a security concerns in 5G. So 5G networks, 5G wireless networks are susceptible to cyber threats, to cyber attacks. For example, there could be some protocol stack vulnerabilities, compromised messages and authentication mechanism, or physical layer attacks. The attackers can generate some malicious RF signals to manipulate the IoT device or base station. So, in order to mitigate these security problems, of course, there are lots of solutions, but one of the most important solution, or one of the most important mitigation method to address the security problems is cryptography. So, we will use, we still use the cryptography to protect the message between transmitter and receiver. The message between transmitter and receiver. So we are using the cryptography to encrypt the message because we are using the unsecure environment. We are using just the RF signals. Anyone can listen these RF signals. So we have to use cryptography. But there's a problem. The problem is that somehow we should increase the entropy pool of the IoT devices, because again, in order to create a reliable, robust, secure random number, we need entropy pool. So in this work, our aim is to use the RF signal in the environment to generate the seeds, or to generate the entropy pool. Okay. So, for this purpose, we used MATLAB 5G toolbox to simulate the environment. These are our parameters. So, we use these parameters to create the spectrograms. After that, we visualize the spectrograms into the 256 and 256 spectrogram images. And these images were generated using a FFT with a length of 4096. Okay, there is an example visualization here, a visualization of spectrogram. So the x-axis shows the frequency and y-axis shows the time. So frequency is from 0 to 256, and this is from 0 to 256. Okay, these are our generated spectrograms using the MATLAB 5G toolbox. Okay, after that, we use this data to generate our seed values. Here we assume that our IoT devices has 5G enabled antennas to sense the RF signals in the environment. So the first step, in order to create the seed value for the random number generation procedure, in order to create the seed value, the IoT device sends the RF signals in the environment. This is the first step. After that, it creates spectrogram like this one, and then it gets a random small random frame from the spectrogram. Here, yes, we are using a randomization here, but this randomization is just a pseudo-random number generated. That's enough for our purposes, because at the end we assume that this part, the extracted part from the spectrogram, is more chaotic than the pseudo-random number generator or generated pseudo-random number. Okay, the next step is to extract some frame, okay, with varying size. But each time we need a random number, we are just selecting one frame from the last spectrogram. Okay, after that, after selecting the frame from the spectrogram, we are using this algorithm. This is our algorithm to create the seed value. There are lots of XOR and shift left, shift right operations to make it more chaotic. Okay, it's a general approach in cryptography to use XOR operations, shift left operations, or shift right operations to create the more unpredictable or more chaotic outputs. Okay, so because our inputs input is just a frame like image. It is not RGB, it's a grayscale image, but the output should be a floating number. Okay, sorry, integer number, not floating number. Floating number. So after getting this data, we are just like input images. We are just reading each pixel in the spectrogram. Then we are performing these operations with the previous pixel value. Okay, so after that we will get a seed value. But again, it is just a seed value. It is not a random number. So after that, we use this seed value in NumPy random function. So as you know, you can change the seed value of the random number generated functions. So this is our seed value. So then we created this heat map to show the entropy values. Okay, in the previous slide, I showed that we are just extracting a frame from the RF signals. So there's a width and height information. Okay, so we can change the height and width information in the input data, in the input spectrogram data. So this heat map shows the different size of width and height information. So after that, we find the maximum entropy value at width value is 32 and height value is 4. And also we obtained the lowest value with width information is 5 and the height information is 2. Okay, but entropy is not enough to calculate the randomness of the generated sequence. We need more tests. So there's an existing test which is developed by NIST SP 822 revision 1, a statistical test suite for random and pseudo-random number generators for cryptographic applications. Sorry, it is not a test, it's a test suite. It contains 15 different tests, as you see here. So, for example, the first test is the Monibit test. It checks the proportion of ones and zeros in the generated sequence and is approximately should be equal. Okay, the number of zeros and the number of ones should be approximately same in the generated sequence. Okay, for example, the second one, frequency test within a block. So here it's like a first test, like a frequency test, but here we are just uh, dividing the sequence into the non-overlapping blocks. After that, we are checking each block, and again each block should have the number of ones and number of zeros. Okay, again there are 15 different tests. We used this test to our random number generator, 5G RF signal based random number generator. This is our results. So we passed 14 of the test. We couldn't pass this one, universal statistical one, but we passed the all remaining tests. So also we check the latency of the our random number generator. So this is our results. So as you see, the generated data or generated random number generation procedure execution time is not too much. It's acceptable, somehow acceptable. So this table shows our best values for each test. For example, for frequency test, for the first test, we obtained the best value with 40 times 40 frame size, and worst value is 30 times 30. Of course, it could be different in if we increase the number of experiments, then of course we can get the more more values, more output values. Okay, so the conclusion and feature work. So in this work, as you see, we use the RF signals in the environment to create the entropy pool for IoT device. This is the idea. And then we use the entropy test and NIST test to check the robustness of our or the quality of the generated random number sequences. So we passed the NIST test, so it means that this method, this approach is acceptable for cryptographic applications. This random number generator is acceptable for the random number cryptographically secure random number generators. Okay, as a future work, we want to focus on exploring the different entropy sources to further enhance the quality of random number generators. Maybe we can use the beamforming inputs, or there are less of MIMO systems. Maybe we can use MIMO beamforming information to generate the data, generate the random numbers, or maybe spectrum sensing or channel estimation. There are lots of applications on RF side, on physical side. Maybe we can use these techniques to use as another or alternative random number or seed generation procedure. Yes, that's all. Thank you for listening.